Instantaneous velocity and instantaneous speed. Throughout its journey, the train traveled at different speeds. It went slow as it passed through the town and the bridge, but went fast otherwise. Previously, we had seen that the average velocity of the train that traveled from station A to station D in an interval of 12 hours was 42 kilometers per hour. Average velocity fails to give us the value at any specific instant of time. It can only tell us how fast a body is moving during a time interval. Physicists use the term instantaneous velocity to describe velocity at any specific instant of time in an object's motion. Instantaneous velocity will tell us exactly what the velocity of the train was when it entered the town or when it was passing over the bridge. Mathematically, instantaneous velocity is the limit of an object's average velocity in an infinitesimally small time duration delta t and is given by v equals limit of the function delta x by delta t as delta t tends to 0. This equals derivative of x with respect to t. In other words, instantaneous velocity is the derivative of displacement with respect to time. We can use the equation v equals dx by dt to compute instantaneous velocity of an object graphically as well as numerically. Instantaneous velocity at any specific point of time in an object's motion is the slope of the position time curve at that point of time. In the example of the train, if we want to find out the instantaneous velocity at t equals 5 hours and 46 minutes, we simply have to find the slope of the tangent. Instantaneous velocity and instantaneous speed. Throughout its journey, the train traveled at different speeds. It went slow as it passed through the town and the bridge, but went fast otherwise. Previously, we had seen that the average velocity of the train that traveled from station A to station D in an interval of 12 hours was 42 kilometers per hour. Average velocity fails to give us the value at any specific instant of time. It can only tell us how fast a body is moving during a time interval. Physicists use the term instantaneous velocity to describe velocity at any specific instant of time in an object's motion. Instantaneous velocity will tell us exactly what the velocity of the train was when it entered the town or when it was passing over the bridge. Mathematically, instantaneous velocity is the limit of an object's average velocity in an infinitesimally small time duration delta t and is given by v equals limit of the function delta x by delta t as delta t tends to 0. This equals derivative of x with respect to t. In other words, instantaneous velocity is the derivative of displacement with respect to time. We can use the equation v equals dx by dt to compute instantaneous velocity of an object graphically as well as numerically. Instantaneous velocity at any specific point of time in an object's motion is the slope of the position time curve at that point of time. In the example of the train, if we want to find out the instantaneous velocity at t equals 5 hours and 46 minutes, we simply have to find the slope of the tangent to the curve at this point. Kinematic equations for uniformly accelerated motion. In this section, we will derive two simple equations of motion relating displacement x, time taken t, initial velocity v0, final velocity v, and acceleration a of an object. You have come across the following equation already in the previous section. V equals v0 plus at. Let us derive two other equations by considering the velocity time graph of an object with the above parameters as illustrated. Area of the shaded portion ABCDO is the displacement x. This equals area of triangle ABC plus area of the rectangle ACDO. Area of triangle ABC equals 1 by 2 into t into v minus v0. Area of ACDO equals t into v0. Therefore, area of ABCDO equals x equals half of v minus v0 times t plus v0 times t. But v minus v0 equals axt. Therefore, x equals half axt squared plus v0xt, or x equals v0xt plus half axt squared. We can rewrite the equation x equals half into v minus v0 times t plus v0 into t, as x equals v plus v0 by 2 into t, which equals average velocity times t. This equation implies that v equals v plus v0 by 2. This equation is only applicable to motion of objects with constant acceleration. The above equation proves that the average velocity is the arithmetic mean of initial and final velocities of an object in a given time interval. As v equals v0 plus at, t equals v minus v0 by a. Therefore, x equals average velocity times t, which equals half of v plus v0 into 1 by a times v minus v0. This gives us v squared minus v0 squared by 2a, or v squared equals v0 squared plus 2ax. The following three equations of motion applicable to motion of objects with constant acceleration are very important and useful in kinematics. V equals v0 plus a times t. X equals v0. Introduction to motion. Movement. Movement is something that defines everything that we see or experience around us. We undergo movement when we walk, run, drive cars, or travel in airplanes. Movement changes position of the object and it can be said to be in motion. Flowing water, formation of clouds, blowing wind, all of these are characterized by motion. Even when we are standing still, we are still in motion because the earth is in motion. It not only rotates but also revolves around the sun along with other planets in the solar system. This solar system itself is in an orbit around the center of our galaxy, the Milky Way. There are three branches of physics that deal with motion of bodies: statics, dynamics, and kinematics. Statics deals with interaction between static bodies. In kinematics, we describe motion of objects without getting into what causes it. On the other hand, in dynamics, we deal with the motion of the body as well as the causes of motion of the bodies. As part of kinematics, in this chapter we will look into what is motion. We will study about motion of objects in a straight line path, namely rectilinear motion. Introduction to rectilinear motion. For training, the police use a firing range where they aim at dummy targets. The bullets fired travel at extremely high velocities. One very peculiar characteristic of their motion is that they travel along straight lines. Even though they are acted upon by gravity, which tries to pull them towards the ground, there is little or no effect on their direction. Therefore, one can easily consider that bullets travel in straight lines. Such motion of any object in a straight line is called rectilinear motion. We shall study different concepts of rectilinear motion like velocity and acceleration in the topics that follow. For simplicity, we shall consider any object to be a point object. Path length and displacement. Frame of reference. When we make a conclusion about different events that we observe around us, it depends not only on what we observe, but also on how we observe the events. Here, we have two people. Let's call them Crash A and Crash B. One would be surprised to see Crash B being able to walk and move around upside down with ease. Also, Crash B, which appears to be inverted, is of the opinion that Crash A is inverted. Now we are faced with a question: who is right? Both of them decide to toss a coin to put an end to the confusion. Person B tosses a coin and catches it. But person A's coin goes straight up and does not return. What do we make of such a peculiar occurrence? There must be something about A that we do not know. Let's try to see the whole picture. It now becomes clear to us that it was crash A who was inverted and not crash B. This brings us to a very interesting subject: frames of reference. Looking at an event from different perspectives leads us to different conclusions. These two different perspectives act as reference states for the two people A and B, and these reference states define the position of objects around them. Such reference states can be called frames of reference. Another interesting scenario to understand frames of reference is as shown. Here, we are able to see someone ambling by the riverside, the gently flowing river water, a boat traveling downstream, and birds flying above. If we consider ground as our frame of reference, we see that all of these objects are moving towards the right with their respective velocities. However, the moment we select any of the moving objects as our frames of reference, we will observe that all the other objects are moving slowly and that the ground is moving backwards. This reinforces the fact that observing from different frames of references redefines the position and motion of objects around. Similarly, to locate any object in space, we require a frame of reference, like a set of axes. Imagine that Mr. Crash resides at the 5th floor of a building, and the city railway station is chosen as the frame of reference. The three axes, X, Y, and Z, can be chosen as shown. The position of his home can be defined as X, Y, Z. But if we are to find out the position of a moving object, like a car, we are faced with a small dilemma. The car will change its position every moment. Therefore, its coordinates are bound to change. If it moves along x-axis, its x-coordinate will change continuously. Similarly, if it moves along the y-axis, its y-coordinate will change. Even its z-coordinate can change with time. Hence, to determine the position of a moving object in space, we not only require three axes and an origin, but also a clock. Position. Let's see how we can describe a car's motion in one dimension with respect to a certain frame of reference. The first thing that we need to do is to consider the frame of reference. The frame of reference is that point from where the car starts moving. This point is known as origin O at t equals 0, x equals 0. According to sign convention, displacements to the right of O are positive and displacements to the left of O are negative. Suppose the car moves from O to the post office, then to the restaurant for having some snacks. Thereafter, they visit the cinema hall to watch a movie. To define the position of the car at various times, we can simply find the distances of these places from O. Hence, the position of the car can be given as O plus 100 meters, plus 220 meters, and minus 80 meters. Path length. Moving forward, with the example of the car, we can define the physical quantity called path length. Initially, the car moves from O 0 to the post office plus 100 meters. Hence, the distance traversed by the car is 100 meters. Thereafter, the car moves from the post office plus 100 meters to the restaurant plus 220 meters. That is, moves forward by a distance of 120 meters. Finally, the car moves towards the left from the restaurant plus 220 meters to the cinema hall minus 80 meters. That is, a distance of 300 meters. Path length is nothing but the total distance traveled by any moving object. In this case, the total distance will be the sum of all the distances. 100 meters plus 120 meters plus 300 meters equals 520 meters. As one can see, the path length is just a value. It does not require direction to be specified. Hence, it is a scalar quantity. Displacement. Moving forward with the example of the car, we can define the quantity called displacement. We had seen that the car starts from O, and after visiting the post office and the restaurant, it eventually ends up at the cinema hall. Displacement of an object is its change in position in a given time duration. We can find the displacement of any object by knowing its initial and final position coordinates in a given time duration. If an object is at x1 at time t1 and x2 at time t2, then its displacement delta x equals x2 minus x1 and the time duration delta t equals t2 minus t1. Physicists use Greek alphabet delta to represent small changes in physical quantities as a convention. In our case, the initial position of the car is O, x1 equals 0 at t equals t1, and the final position of the car is C, x2 equals minus 80 meters at t equals t2. Hence, the displacement of the car can be calculated as x2 minus x1 equals minus 80 minus 0 equals minus 80 meters. If the car wouldn't have moved beyond the post office, the displacement would have been x2 minus x1 equals 100 minus 0 equals 100 meters. As we can see, displacements could be positive as well as negative, depending upon the direction in which the body has traveled. Hence, it has magnitude as well as direction, and hence is a vector. Here, if the car would have returned back to O instead of going to the cinema hall, the initial as well as the final position would have been the same. Therefore, the displacement of the car, which is the difference between the initial and the final position of the car, would also be 0. However, the path length would not be 0, as the car has traveled a distance of 220 meters and back. That is, a distance of 440 meters in all. Position time graph. We can represent rectilinear motion effectively using position time graphs. Let's take up the example of the car that visits the post office, the restaurant, and the cinema hall, all of which lie along a straight line. We have already seen that the position of the car at these locations can be given as 0, plus 100 meters, plus 220 meters, and minus 80 meters, respectively. Let's assume that the time required by the car to visit these places be 0 seconds, 8 seconds, 16 seconds, and 30 seconds, respectively. We now know the positions of the car at different instants of time. Let the y-axis represent the position of the cars and the x-axis represent the time in seconds. We plot the corresponding points on the graph. We can now connect all these points by drawing a curve that passes through all of these points to obtain the position time graphs. Imagine a situation where the car travels straight to the restaurant without taking any stops in between. If we also consider that the car travels equal intervals in equal intervals of time during this journey, its position time graph will be a straight line with a constant slope. Such motion of the car is called uniform motion. The previous case, where the car could not travel equal intervals in equal intervals of time, is a case of non-uniform motion. Average velocity and average speed. As we have already seen, there are a lot of bodies around us that are in motion. Some of them move really slow, like the snail. On the other hand, some of them move really fast, like the train. Speed gives us a measure of how fast or slow a body is moving. The speedometer in our cars, or any other automobile for that matter, tells us how fast or slow the car is moving. We shall now be understanding the concept of speed and average speed in terms of physics. Imagine that a train has to travel from a starting point, station A, to a destination, station D. The total distance between A and D is 500 kilometers. But before it reaches the destination, it has to pass through a town and also cross a bridge. It starts off at 6 a.m. in the morning. Initially, it travels pretty fast, but as it enters the town, it has to slow down to avoid any accident. Once past the town, it has to slow down again as it approaches the bridge. After crossing over the bridge, the train has the liberty to travel at a faster speed. Finally, it reaches the destination at 6 p.m. in the evening. Throughout its entire journey from station A to station D, the train has traveled at different speeds at different times. Physicists use the term average speed to describe as to how fast an object moves over a period of time. In our case, the train travels 500 kilometers in 12 hours, 6 a.m. to 6 p.m. Hence, the average speed of the train is 500 by 12 equals 42 kilometers per hour. Here, we have considered the path length or the actual distance traveled by the train. The path length is always a positive value as it is not bound by any sign convention. Therefore, speed will also be a positive value. If the train would have returned to town at 4 a.m., which is just 100 kilometers away from A after it has visited station D, the average velocity and the average speed would have been different. Average speed would be 500 plus 400 by 12 plus 10 equals 900 by 22 equals 41 kilometers per hour. However, average velocity depends on the displacement, which in this case is x2 minus x1 equals 100 minus 0 equals 100 kilometers. And this displacement occurs in 12 plus 10, 22 hours. Average velocity is defined as the displacement or change in position delta x of an object divided by the time interval delta t during which it has changed its position. It is given by v equals x2 minus x1 by t2 minus t1 equals delta x by delta t. The bar over v is a notation used to represent that it is an average quantity. Hence, the average velocity of the train is 100 by 22 equals 4.5 kilometers per hour. The SI unit of velocity is meters per second. However, in everyday circumstances, we use kilometer per hour. As velocity involves direction, it is a vector quantity and sign convention is applied just like in displacement. Position time graphs for average velocity. If we are to plot a position versus time graph, it can be done as shown here. Average velocity of the train for any time interval can be found out from the graph. The slope of the curve between any 2 points P1 and P2 can give us the average velocity of the train during a time interval. If the train would have come back to station A, the initial and the final positions of the train would have been 0. Hence, in such a case, the displacement and hence the average velocity would have been 0. Similarly, if there would have been no town or no bridge lying in the path of the train, it could have covered the distance at some constant speed. In that case, the position time graph of the train would have been in a straight line. In case the train would have halted in between due to some technical problem, then its position would remain constant. In that case, the position time. Whenever we come across the word acceleration, we think of high-speed cars moving at blinding speeds. The concept of acceleration equally applies to any object that is in motion. Consider a situation where you are hungry and want to get to the nearest fast food joint. You get into your car and start driving. Obviously, the car will be able to gain a certain velocity only gradually. Eventually, the car attains a certain velocity and keeps moving at that velocity. As soon as you realize that you are nearing the fast food joint, you slow down your car and slowly get the car to a stop. Throughout your short journey to the fast food joint, your car traveled at different velocities at different times. Its velocity increased initially, and then stayed constant for some time, and then decreased as it reached the restaurant. This change in velocity of a moving body over a time interval is known as average acceleration. Mathematically, it is expressed as a bar equals v2 minus v1 by t2 minus t1 equals delta v by delta t, where v1 is the initial velocity of the car and v2 is the final velocity of the car. From this expression, the SI unit of acceleration can be derived as meter per second square. In the first case, v1 is 0, since the car is not moving initially, and v2 is some positive value. Hence, the acceleration is positive. In the second case, v1 is the same as v2, since the car is moving with a constant velocity. Hence, its acceleration is 0. In the third case, v2 is 0, since the car comes to a stop finally, and v1 is some positive value. Hence, the acceleration of the car is negative. Velocity time graphs. If we are to plot these three cases onto a velocity versus time graph, we get the following. In the first case, since the velocity is increasing with time, the graph will be an increasing curve. In the second case, since the car moves with a constant velocity, the graph will be a horizontal line parallel to the x-axis. Finally, in the third case, since the velocity decreases with time, the graph will be a decreasing curve. The average acceleration in a velocity time graph is defined as the slope of the line connecting any 2 points, v1, t1 and v2, t2 on the graph. The SI unit of acceleration is meter per second square. Acceleration can be positive, negative or 0. If an object increases its velocity, it has positive acceleration. If it moves with constant velocity, it has 0 acceleration. If it decreases its velocity, it has negative acceleration, also known as deceleration or retardation. It is important to note that 0 acceleration does not mean that the object is at rest.
Instantaneous acceleration. Let us say if one wants to find out the acceleration of the car at some instant t, then the slope of tangent to the curve at that point gives the value of instantaneous acceleration. Mathematically, alpha is equal to limit delta t tends to 0 delta v by delta t, which equals dv by dt. Let us see position time and velocity time graphs of a few objects. The object moves in the positive direction with a steady increase in velocity. The slope of the velocity time graph shows that the acceleration is constant and positive. Average acceleration equals delta v by delta t equals 24 meters per second by 15 seconds equals 1.6 meters per second square. The object moves in the positive direction with a steady decrease in velocity. The slope of the velocity time graph shows that the acceleration is constant and negative. The average acceleration equals delta v by delta t equals minus 20 meters per second by 15 seconds equals minus 1.33 meters per second square. The object moves in the negative direction with a steady decrease in velocity. The slope of the velocity time graph shows that the acceleration is constant and negative. Average acceleration equals delta v by delta t equals minus 30 meters per second by 15 seconds equals minus 2 meters per second square. Apart from deducing acceleration, we can use velocity time graph in finding the displacement undergone by an object. In a velocity time graph, the area under the curve corresponding to any time interval represents the object's displacement during this time interval. This is the velocity time graph of an object's motion with constant velocity, that is 0 acceleration. The shape is a rectangle. Area of a rectangle equals length into breadth. Hence, displacement equals 6 seconds into 30 meters per second equals 180 meters. Obviously, you can also calculate the acceleration using the term delta v by delta t. In this graph, the area enclosed is a triangle. Hence, the displacement equals half into base into height, which equals half into 6 seconds into 40 meters per second equals 120 meters. In this graph, the area enclosed is a trapezoid. Hence, the displacement equals half into breadth into height 1 plus height 2 equals half into 4 seconds into 20 plus 40 meters per second, which equals half into 4 into 70 meters, which equals 140 meters.
Velocity. Imagine that you are standing on a railway platform and a really fast train zooms past. But when the same train passes by a moving train, it appears to be running slower. However, that is only because both the trains are moving along the same direction. As the train in which the viewer is seated is also moving, the other faster train's velocity does not make much difference, whereas to a person on the ground, the other train moves with a much greater velocity as the person is static. In order to understand such phenomena, which you may have yourself experienced, we need to know an important concept known as relative velocity. To understand the concept of relative velocity mathematically, we consider two cars, A and B, which are to move along the x-axis with velocities VA and VB. Initially, both of them are positioned somewhere along the x-axis. Their positions are xa0 and xb0 respectively at time t equals 0. After some time t, both of them would have traveled some distance. Car A would have traveled a distance of VA into t, and car B would have traveled a distance of VB into t. Let their positions be given by xa of t equals xa of 0 plus VAT, xb of t equals xb of 0 plus VBT. In order to find the relative velocity of car B with respect to the observer in car A, we need to calculate the displacement of car B with respect to car A in time t. xba of t equals xb of t minus xa of t equals xb of 0 plus vbt minus xa of 0 plus vat equals xb of 0 minus xa of 0 plus vb minus va into t. This equation means that to an observer in car A, car B would have a velocity Vb minus Va. This is because this is the rate of displacement from A to B. That is, velocity of car B relative to object A is Vb minus Va. That is, Vba equals Vb minus Va. Similarly, velocity of car A relative to car B is Vab equals Va minus Vb. The above two equations are applicable even if Va and Vb are instantaneous velocities. Let's see some special cases of relative velocity. When two cars A and B move with the equal velocities, here Va equals Vb, that is, Vb minus Va equals 0. Hence it follows that xb of 0 minus xa of 0 equals xb of t minus xa of t. From the graph, it implies that this is the constant distance maintained between the two objects. The position-time graph of the two objects is illustrated here. The graphs of the objects are parallel lines. In this case, the relative velocity Vab or Vba is 0. There is no relative motion between the two cars.
When object A moves with a greater velocity than object B, here Va is greater than Vb, therefore Vb minus Va is negative. Let Va equals 20 meters per second and xa at time 0 equals 10 meters. Vb equals 10 meters per second and xb at time 0 equals 50 meters. The distance covered by both the cars can be calculated as shown. Vb minus Va is less than 0. From the table, we are able to see that after a period of 4 seconds, both the cars would have covered a distance of 90 meters. Hence, even if we plot graphs of the data, they will intersect at t equals 4 seconds. We can observe from the graph that the slope of line A is steeper than that of line B. VBA equals VB minus VA equals 10 minus 20 equals minus 10 meters per second, which is equal to minus VAB.
When objects A and B move in opposite directions with different velocities, as they move in opposite directions, VA and VB will be of opposite signs. Suppose car A starts at XA of 0 equals 20 meters and move with a steady velocity VA equals 20 meters per second, and car B starts at XB of 0 equals 100 meters and moves at a steady velocity VB equals minus 20 meters per second. Negative velocity indicates that the object is moving in the opposite direction. For simplicity, we take up the direction to the right as positive and that towards the left as negative. The distance covered by both the cars can be calculated as shown. From the table, we are able to see that after a period of 2 seconds, both the cars would have crossed each other. Even if we plot a graph of this data, we will find that both the graphs meet at t equals 2s. Velocity of B relative to A equals VBA equals minus VB minus VA equals minus 20 equals minus 40 meters per second equals minus VAB. Here we see that the magnitude of the relative velocity VAB or VBA equals 40 meters per second is greater than the velocity of A 20 meters per second or velocity of B minus 20 meters per second. To conclude, if two objects are moving along the same direction, magnitude of the relative velocity is less, as it is the difference of the two velocities. If two objects are moving in opposite directions, magnitude of the relative velocity is more, as it is the sum of the two velocities. An ambulance moves from point A to C in 25 seconds, where distance between A and C is 500 meters, and returns from point C to B in 15 seconds, where the distance between C and B is 225 meters. Calculate the average speed and average velocity of the ambulance from A to C and back to B. Solution: A to C. Average velocity V average equals displacement by time interval equals 500 by 25 equals 20 meters per second. Average speed equals total path length by time interval equals 500 by 25 equals 20 meters per second. Here, the average speed equals the magnitude of average velocity. A to C and back to B. Average velocity V average equals displacement by time interval equals 500 minus 225 by 40 equals 275 by 40 equals 6.875 meters per second. Average speed equals total path length by time interval equals 500 plus 225 by 40 equals 725 by 40 equals 18.125 meters per second. Here, average speed is not equal to average velocity.
Example 3.2. An object O is governed by the following law of displacement. X equals AT plus BT square, where x is the displacement along the x-axis. A equals 7.2 meters per second. B equals 2.5 meters per second square, and t has a unit of seconds. Find the velocity of O at t equals 0 seconds and t equals 5 seconds. What is the average velocity of the object O between t equals 3 seconds and t equals 5 seconds? Solution. Using calculus, velocity is v equals dx by dt equals d by dt of at plus bt square equals a plus 2bt. Thus, velocity at t equals 0 is vt equals 0 equals a plus 2b into 0 equals a meters per second, which equals 7.2 meters per second. And vt equals 5 equals a plus 2b into 5 equals a plus 10b equals 7.2 plus 25 meters per second equals 32.2 meters per second. Average velocity equals x into 5 minus x into 3 upon 5 minus 3, which equals 5a plus 25b minus 3a minus 9b upon 2, which equals 2a plus 16b by 2, which equals a plus 8b meters per second, which equals 27.2 meters per second. Example 3.3. Using calculus, write the equation of motion for any object O with a constant acceleration a and initial velocity vi at time t equals 0. Solution. We have a equals dv by dt, implying dv equals a into dt. On integration, integral dv from vi to v equals integral a dt from 0 to t, or v minus vi equals a integral dt from 0 to t as a equals constant, or v minus vi equals at, or vt equals vi plus at. Also, v equals dx by dt, or dx equals v into dt, or integral dx from xi to x equals integral v dt from 0 to t, or x minus xi equals integral of vi plus at dt from 0 to t equals vi plus at square by 2, or x equals xi plus vit plus half at square. Again, a equals dv by dt, which equals dv by dx into dx by dt, which equals v dv by dt, or v dv equals a dx. Hence, integral of v dv from vi to v equals integral of a dx from vi to v, or v square minus vi square by 2 equals a into x minus xi, or v square equals v square plus 2a into x minus xi.
As shown in the figure, a person throws a rubber ball with an initial velocity vi from the top of the building. Calculate the maximum height d the ball will achieve and also how long it will take to hit the ground. Assume g equals 10 meters per second squared. Solution. Using the equation of motion, we get Vf square equals Vi square plus 2AD and A equals minus G and Vf equals 0. Hence, Vi square equals minus 2AD, or 10 square equals minus 2 into minus G into D, or D equals 100 by 2 into 10, or D equals 5 meters. Hence, the ball will rise to a distance of 5 meters from the top of the building. Placing the coordinate axis, we fix the initial position of the ball at 0, 15 on positive y-axis. Final position of the ball is 0, 0. Hence, yf equals yi plus vit plus half at, or 0 equals 15 plus 10t minus half gt square, or minus 10t plus 5t square minus 15 equals 0, or t square minus 2t minus 3 equals 0, or t equals 3 or t equals minus 1. Hence, t equals 3 seconds.
Example 3.5. Analyze the motion of a body under free fall. Assume that there is no air resistance. Solution. Under free fall, an object accelerates because of the acceleration provided by the gravitation of the Earth, which is called g, and is equal to 9.8 meters per second square. As we can neglect the air resistance, there is no other retarding force for an object under free fall. We can consider g to be acting constantly if the height through which the object is falling is small as compared to the Earth's radius. Hence, in other words, we can say that free fall is nothing but a case of uniform acceleration. Assuming that the object was released with an initial velocity vi of 0 and acceleration a equals minus g, and y is the displacement of the object under the free fall, the three equations of motions can be written as vt equals 0 minus gt equals minus 9.8 meters per second, yt equals 0 minus half gt square equals minus 4.9 t square meters, v square equals 0 minus 2gy equals minus 19.6y meters square per second square. Variation of a equals g with time t, and variation of v with time t, and variation of y with time t can be seen here.
Show that the successive distances traveled by a free-falling body is in the ratio of odd natural numbers. Solution. Assuming that the free fall started at t equals 0 with an initial velocity of vi equals 0, then by the equation for displacement y yt equals minus half gt squared. Now, choosing a small period of time delta t and calculating the displacement for each successive delta t and assuming yt equals minus half g delta t square equals yf. The distance covered by a moving vehicle after the application of brakes is called the stopping distance of the vehicle. Derive an expression for the same in terms of the initial velocity vi and acceleration a. Solution. Let the distance traveled after the application of the brakes be yd. Thus, using the equation for motion and noting that the final velocity vf equals 0, vf square equals vi square minus 2ayd, or vi square equals 2ayd. Hence, yd equals vi square by 2a. We see that the stopping distance is directly proportional to the square of the initial velocity and inversely proportional to the acceleration. An earthen pot was accidentally dropped from the 5th floor of a building, which is at a height h of 20 meters. How much time will a person standing on the road directly below have to react before the pot hits the ground? Assume g equals 10 meters per second square. Solution. Considering that air resistance is negligible, the initial velocity vi of the pot is 0. The pot experiences a uniform acceleration g. We have h equals half gt square, or t equals root 2h by g equals root 2 into 20 by 10 equals root 4 equals 2 seconds. Thus, the person standing on the ground has exactly 2 seconds to react. Two trams in London are moving in a direction parallel to each other. Tram 1 moves with a speed of 36 km per hour towards the east, and Tram 2 moves towards the west with a speed of 18 km per hour. What is the velocity of Tram 2 with respect to Tram 1? What is the velocity of the ground with respect to Tram 2? What is the velocity of a man running inside Tram 1 in a westward direction with a speed of 9 km per hour with respect to Tram 1 as observed by a man on the ground? Solution. Assuming the east direction to be the positive x-axis, the respective velocities of the trams are v1 equals 36 kilometers per hour equals 10 meters per second. v2 equals minus 18 kilometers per hour equals minus 5 meters per second. v21 equals v2 minus v1 equals minus 15 meters per second. Relative velocity of the ground with respect to tram 2 is v ground minus v2 equals 0 minus v2 equals 5 meters per second. Let Vm be the velocity of the man with respect to ground. Hence, Vm1 equals Vm minus V1 equals minus 9 kilometers per hour equals minus 2.5 meters per second. Thus, Vm equals minus 2.5 plus V1, or Vm equals 10 minus 2.5 meters per second equals 7.5 meters per second.